Warm greetings to everyone. Today we are going to see a topic particularly in linear algebra, that is nothing but a linear transformation. Usually in set theory we connect two sets by a function. So whatever may be the algebraic structure we are defining in set theory, that could be extended to whatever may be the algebraic structure we are extending. So that kind of one application is nothing but this linear transformation, because in set theory we are connecting two functions. We are connecting two sets by a particular function with a specified definition, and that kind of application is in vector spaces. So here we are going to connect a linear transformation to vector spaces through a linear transformation. Here I am taking V as a vector space and W as a vector space, and we are connecting that vector space through a mapping or a function named as a linear transformation, provided this transformation should have some property that is every zero vector of the domain vector space should be mapped to the codomain zero vector of the codomain vector space. And in the same way, this should satisfy the condition, that is every vector space should satisfy two conditions. One is vector addition and the another one is scalar multiplication. As in a vector space, this linear transformation also should satisfy the condition that is vector addition, that could be equal to t of x plus y should be equal to t of x plus t of y. And in the same way, the scalar multiplication can be t of cx is equal to c into t of x. And of these both conditions, we should have these x and y from the domain vector space V, and the scalar c should be from F, provided each of the vector spaces should be defined from the field F. So that I am taking the scalars from the field. And if a transformation or if a mapping defined between these two vector spaces V and W, and this transformation is satisfying all these conditions, then I can say this transformation could be a linear transformation. But in all cases we cannot see all the three conditions. So in precise we are going to see these three conditions together, so that we are going to define such kind of condition, that is vector addition and scalar multiplication together. So that can be defined as t of cx plus y is equal to c into t of x plus t of y for the linear transformation t from V to W, provided I am taking these x and y from the domain vector space V, and as usual the scalar is from the field F. So if we are checking this condition alone, then we can define a particular transformation as linear. For example, I am going to give some transformation. So one particular transformation is T is a transformation from two-dimensional vector space R2 to the same two-dimensional vector space R2. And here the definition will take place as T of A1, A2 is equal to 2A1 and A2. We can now check whether this definition will give you a linear transformation or not. For this, I am going to take two elements. One is x, that is A1, A2. The other one is y, and that can be defined as B1, B2. So y can be here as B1, B2, and these two elements I am taking from the domain vector space V. That is domain vector space, in particular it is two-dimensional vector space R2. So let me going to check, that is whether this transformation from R2 to R2 will satisfy this condition. T of cx plus y is equal to c into t of x plus t of y. Yes, we can check. And we have defined here x as a1, a2 and y as b1, b2, and this condition should be checked. That is, for every two-dimensional vector, if you are applying in the transformation T, we can get 2a1 and 2a2. So let me go for the checking. So that now this transformation T of c into x plus y will act as T of, we have defined our x as a1 comma a2, so cx will be ca1 comma CA2 plus, and this is an order pair since it is a two-dimensional vector space. This is an order pair, and this one y will be y1, it is b1 and b, and we can add these things so that we would, and our definition is T of a1 a2, that is first component of this vector should be multiplied with 2a, and first we have to add these things, then we have to apply the linear transformation application. So this thing will be, and usually the two-dimensional vectors could be added component wise, so the first component should be added with the first component of the second vector. This can be T of CA1 plus B1 comma CA2 plus B2. Yeah. And our linear transformation application is first component should be multiplied with 2. So that could be 2 into CA1, 2 into CA1 plus B1, and the second component is CA2 plus B2. Okay, but we need, as I told you already, that is wherever we are applying this transformation, T of x plus y will provide you C into T of x plus T of y. We have given a transformation, but whenever this transformation satisfying this condition, we can say this transformation will be a linear transformation. But here we cannot check that transformation as C into T of x plus C of y. So that this could not be, and this is not equal to C into T of x plus T of y. So in this condition, our given transformation is mapping from a vector space to vector space, but this cannot satisfy the conditions of a linear transformation. So let me go for another example which is definitely satisfying the conditions of linear transformation. So one such definition is T is a transformation from set of all matrices of n by n order over real number set to the same vector space. Set of all matrices of order n by n over real number set. And here I am defining the transformation definition as T of A will map all the matrices to A transpose. So here we can check whether the given transformation is linear or not. For that I am taking two matrices, one is A, the other is B, from the domain vector space n by n matrices over R, and the scalar C from the real number set. Okay, and with these applications, I am going to find what is my CA plus B, and I am going to check what is my CA plus B. And as we know, vector space always satisfies the conditions of vector addition and scalar multiplication. So whenever I am multiplying a scalar with the n by n vector and n by n matrix, and this could also be an element of the domain vector space, and again this could also be an element of the domain vector space. So in general I can choose this matrix is again an element of m by n matrix, m by n vector space. And now we are going to apply the transformation condition T of A is equal to n A transpose for this element, this matrix CA plus B. And as we know, A is an n by n matrix, B is an n by n matrix. So CA plus B is also an n by n matrix, and this is also an element of the domain vector space set of all matrices from R. Okay, so I am applying the transformation definition here. So T of CA plus B will give you the result CA plus B the whole transpose. Okay, so I am going to apply the transformation for each and every matrices. So this can be written as CA transpose plus B transpose. As the C is a scalar, we can again define this as C into A transpose plus B transpose, and now this C into A transpose can be C into T of A plus this B transpose would be T of B. And now I have T of CA plus B is equal to C into T of A plus T of B. So now we have defined a transformation which is a linear transformation from a domain vector space to codomain vector space. So whatever may be the transformation, we are defining from vector space to vector space, and the dimension of the domain vector space and dimension of the codomain vector space may also differ, but that should satisfy the condition C of T of Cx plus y is equal to C into T of x plus T of y. So such kind of transformation alone will bring us a linear transformation condition. Next important aspects are the identity transformation and zero transformation. So whatever may be the transformation I'm defining, that can be a linear transformation. And so far we are checking what are the conditions for a defined mapping to be a linear transformation. Now we are going to consider a linear transformation, and with that linear transformation, whatever may be the conditions we can impose to find a zero transformation or identity transformation. So first I am going to define a transformation from V to W. Okay, and in particular, if I am having I am choosing an element small v, that is it is a vector from the domain vector space in capital V, that is I am choosing a vector from the domain vector space, and if it is satisfying the condition T of V is equal to V, and this is a linear transformation. If it is satisfying the condition, that is whatever may be the element I am choosing from the domain vector space, that should be mapped to the same element. So for satisfying this condition, my codomain vector space should be V also. So if I am having such kind of transformation, then I can say that is a identity transformation on V. That is such kind of transformation, identity transformation on V. So for defining an identity transformation, the transformation should have domain and codomain vector spaces as same vector spaces. Otherwise, if we are having distinct vector spaces as domain and codomain, we cannot define the identity transformation. And in the same case, we are defining zero transformation. Again, I am going to define a transformation from V to W, and in this transformation, I am choosing a vector V from the domain vector space. And if I am having the condition, whatever may be the vector I am choosing from domain, that should be mapped to zero vector of codomain. Okay, if I am having such transformation, then I can call this transformation as zero transformation. And as I told you already, these are all linear transformations that can be checked. And these true transformation, that is both identity transformation and zero transformation, will definitely satisfy the conditions of linear transformation. So that only we are just applying the condition or applying the mapping definition alone. And these two conditions are zero transformation and identity transformation. With these, we are going to define a particular definition. Those are rank of T and nullity of T. With these two definitions, I am going to define those conditions. And for that, one such important definition is range space. If I am having a transformation T from V to W, the range space of T can be defined. Whatever may be the element from domain, I should have some image in codomain. So those kind of elements will be in the range space, and rank of T would be defined as dimension of range space of T. So whenever we are using the terminology as dimension, we know range space of T is also a subspace, and it is a subspace of the domain vector space. So if we can find the dimension of the range space of T, and that can be defined as the rank of the linear transformation. And in the same way, nullity of T can also be defined. Again, I am choosing a transformation T from P to W, and here null space. Null space is set of all elements I am choosing from V, that is domain vector space, and those are all the elements are satisfying T of D is equal to 0, provided this 0 is a 0 vector of the codomain vector space. So such kind of elements will form null space, and since it is a null space, it is the subset of the domain vector space. So as it is a subspace, we can find the dimension of the null space also. So dimension of null space means this can be denoted as n of t. So dimension of null space can be called as nullity of t. With the small introduction of linear transformations and some examples and definition of range space and null space, we can conclude the topic linear transformations. So thank you everyone.